This is a very, very convenient test to have in mind whenever you need to test a series for absolute convergence. So the ratio test works like this. You're going to take your series, it's like the sum of an from n equals 1 to infinity, and you're going to divide consecutive terms. So the n plus 1th term divided by the nth term. So the third divided by the second, or the fourth divided by the third, or the 1,001st term divided by the 1,000th term. And you're going to take the limit of that when n goes to infinity, of this fraction, of the ratio between consecutive terms when n goes to infinity, and you're going to find the number L. If you have that limit equals L, depending on the value of L, you can make the following conclusions. If L is less than 1, then you can say for sure that the series converges absolutely. Let's ignore the absolute portion for a second and understand why that's the case. Let's just pretend like, assume for a second that ANs, that they're non-negative, so that the absolute value is just AN. And what happens if this limit is L? I'll call it R, and you're going to see exactly why. Let's say L equals R, you're going to see exactly what's going on. If the limit is the case, it is equal to L. That means for very large n, that fraction needs to be close to L. So that means I'm calling it R. So I'm going to write an plus 1 not equal, right? Approximately R. So if I take this and move it over, an plus 1 is approximately an times R. Yeah. Of course, what does that mean? What does that mean? If I'm adding my terms like this, then sure, at the beginning I don't quite know, because what I'm saying, it only works for very large n. But later on, when I'm adding, again, maybe 100, 101, 102, maybe it needs 1,000, maybe it needs more terms. Because every term is approximately the previous term times R, then if maybe I ignore a few terms here, and from the 100th term, I start writing that this is approximately 100 times R, and then to go from here to there, this approximation, 100 times R squared, 100 times R cubed. This is approximately going to be geometric. With ratio R. So the idea behind the ratio test is that you're comparing your series to a geometric series with that ratio. So if you go back, you can see that ratio L less than 1 is equivalent to comparing your series to a ratio test, to a geometric series with ratio less than 1. So you can think of this as a limit comparison test that's built into the series without you having to think about what geometric series to compare it to. And so, of course, whenever L is greater than 1, then you have a comparison with a geometric that's divergent, so your series will also diverge. And whenever L equals 1, that's a problem, because you may have a ratio of -1 of sorts, but that could end up making your series not converge absolutely, but converge conditionally. So because that case is weird, the test is going to be inconclusive. There are series that are convergent, and there are series that are divergent for which the ratio test will give you L equals 1 in both cases. So you can't know for sure. And of course, I can add the absolutely without any issue now, because I'm dealing with a series that's already taken absolute values. So this is the idea of the ratio test. I think is very simple. Let's solve a few examples to see how it works. The examples we can solve are very, very nasty looking if you look at them for a second. Let's take a look at an here at the first term. That's the first series here, excuse me. Whenever I see factorials, I'm immediately thinking maybe the ratio test can help me out here. So all terms here are positive, but even if they were, I can just go ahead and apply absolute values to check what's going on. And so the limits when n goes to infinity of an plus 1 over an, I'll write absolute values just so people know that I can, but it doesn't matter because the an's are all positive. So the an plus 1 is just me replacing n with n plus 1, so I end up with n plus 1 to the power n plus 1 over n plus 1 factorial divided by n to the power n over n factorial, like this. So I got to calculate this limit. Hopefully that's going to be something that's less than 1. So let's see. This is the limit. N goes to infinity. Repeat the first fraction divided by n plus 1 factorial. And then flip the second fraction upside down as n goes to infinity. So the reason why the ratio test is helpful with factorials is that things cancel out very nicely. So you can see, if you remember that factorials are, if you remember that n plus 1 factorial, more precisely, is n plus 1, and then times n, and then times n minus 1. And then times n minus 2, and then times n minus 3, and so on. Everything that's left over here is n factorial. And so I get to cancel this and have an n plus 1 left over here. Yeah, right here at the bottom. There's an n plus 1 left over. And I can also look at the top here, n plus 1 to the power n plus 1. I wish I could combine these two. I wish I could combine these two. And I will by doing this. I'm going to rewrite the top, just the top, as n plus 1 times n plus 1 to the power n. And then n to the power n stays at the bottom right here. This, now that I already have the conclusion that I need for it, I'll move it over to that side. And I hope that you see that the top of the fraction is the same as it was before, just adding the powers of the n plus 1 to the power 1 and n plus 1 to the power n. These I can write under the same exponent. And this will be n plus 1. I get to cancel them. So I get to cancel these two. But this stays as it is, and this is the limit when n goes to infinity of 1 plus 1 over n to the power n. This may seem like a difficult limit, but this is a known limit. This is known. To be E, Euler's number. So this is E, which is greater than 1. If you don't know how and why this is E in some books, this is how you define the number E. I can maybe prove this to you in a separate video, but this is a limit that you should remember, that this is known to equal E. If you don't, just go maybe on a formula sheet somewhere, write down this is going to be helpful. This is known to equal E. And E is greater than 1. It's 2.72 more or less. So the series diverges. Series diverges here. Let's work on the second series. One interesting thing that you can do here before I solve the next example, look again at the beginning. This diverges because you ended up with an e as your limit. But if you flip it upside down, have the factorial at the top, it will converge, because if you repeat the calculations, you're going to get 1 over e for your limit, and that's going to be less than 1. So another very, very interesting idea. And because of that, remember the test for divergence, right? I know this converges, and so I also know that this is, what's that limit? The limit of n factorial over n to the power n. It needs to equal 0, because if it didn't equal 0, then that series would have to diverge by the test for divergence. So something that I can be sneaky about is just ask you, a teacher can do that, right? Ask you on a test or an exam, find this limit. It's hard because you have factorials and n to the power n in here, but how can you prove to somebody that this limit actually equals 0? You can just show that this series converges. Just come up with the series out of nowhere. Show that it converges because why not, right? Of course it does, by the ratio test. And then conclude that by the test for divergence, the limit has to equal 0. Because if it didn't equal 0, then your series would diverge. This is sort of a sneaky way to ask you to check that you understand these limits correctly, these tests correctly. Here's another one, pretty easy with the ratio test. Limit of an plus 1 over an. So again, at the top, I make n slightly bigger by adding 1 to it. And then divide by the regular version, which is the same as multiplying by the reciprocal of the regular version. And now these I get to cancel. There's a 3 left over at the bottom. And so there's a 3, 1/3. And then the other 2 I get to combine under the same denominator. Now this is going to 1 for sure, but it's not the same as it was before. Before, the exponent was also growing to infinity. It's 1 to the power of infinity, which is an indeterminate form. But this is just 1 squared. This is 1 squared. There's no question here. This is just 1/3, which is less than 1, so the series converges. And more than that, it converges absolutely, because that's what the ratio test can tell us. Let's try the next one. I wonder what will happen to this one. Again, the top of the fraction will be n plus 1 to the power 100, and 100 to the power n plus 1, n plus 1 factorial, and then the bottom of the fraction, which I'm already flipping upside down, I'm already inverting, will be just the regular fraction, the regular general term of the series. I get to cancel some of these out. These give me an n plus 1 in here. So there's an n plus 1 there. These I can again write under the same exponent. I can write n plus 1 over n to the power of 100. And then these I can cancel out as well to get a 100 left at the top. So there's a 100 right here. And so that is what I get. I'm taking the limit of this. That wasn't very neat. Taking the limit of this when n goes to infinity. So this is 0, 100 divided by infinity, times, and this is 1 to the power 100, which is just 1. So the limit is 0, which is still less than 1. So the series converges absolutely. Pretty interesting, huh? Which is also, again, very surprising. What if your teacher goes and says, find the limit of this thing, n to the power 100, 100 to the power n over n factorial? It has to be 0. And it has to be 0 because that's the general term of a convergent series.